second speaker is Dan Xie from Tsinghua. He's going to tell us about the duality of Fourier to 1 gauge 3.
Okay. Thanks very much for the invitation. I'm going to talk about the duality of 4-dimensional n equals 1 gauge. So this is one work with my students for your and thinking. They're both graduate students. Okay, so for the duality of 4-dimensional n equals 1 is probably I should call them cyber like duality. So those are the duality which originally discovered by cyber. So it basically claims that the P theory to asymptotically free theory, which will flow to a same fixed group. So those theories are the UV theory. Two UV theory are quite different. They are certainly not equivalent in any sense, but at the low energy, they will flow to the same fixed group. So that's so what Julia just said. The same kind of IR theory. So there's some examples, early examples. All of them were discovered in the dualities. So one example is SQCD. So this is probably the most familiar ones. Probably many people use this. Right? And then Kutashov and Schweimer, they kind of generalized to the case SQCD with a single adjoint hybrid model. I will talk about details of those dualities. Also discovered just right after cyber. So this is probably many of know this duality. Then there is a much less known duality that involves SQCD plus 2 adjuncts. And the model has a specific superpotential, which I'll talk about later. Here also, for the Kutashov-Schweimer duality, one also have a superpotential. The superpotential relation. 不是柔。And in well, this all discovered or discussed before the 1997, where the ADS-MT comes in play. So after that, people just forget about it. Until 2000. Maybe around 2014. Okay, by Kutashov, which I believe is very less known, maybe just 10 citations. Again, this is a model with that probably is called exclusivity plus 2 actions. And also a suitable. Oh, these are basically the long models with the duality property. Namely, you have a one model, and then you can find a dual model which will flow to the same 6 points. And also, I will mention that there are other very similar models. With the other gauge groups. For all of those 3 classes, the gauge group is basically SU type gauge groups. For people also generate the discussions to other gauge groups, such as other classical gauge groups, and more difficulty, one can have exceptional gauge groups. So those are the non-duality models with the dualities. And our goal is try to generalize those considerations and try to construct models with more models with duality properties.
If you think it's hard to see, you can just use a lot of empty.
Okay, I try to.
So you can comment something.
I try to. Okay. So let me review the essential features of all those dualities. They are all similar. So I will first I will write simply draw a picture. So those are the models. One of the so these are gauge nodes. So this is the SUNC gauge group. It couples with a pair of NF fundamental layers. But so I need to have the same number of fundamental and anti-fundamental chiral fields to cancel the chiral around. And then I can add the accurate. Those are the accurate chiral fields. So here I write 2. So we can have asymptotic frequency. But in principle, one can add the arbitrary number. So those are these are basically cover all those models with the SUNC gauge groups. And the dual model actually has a similar structure, but with some essential difference. So the gauge group actually changed, and also we need to change the orientation of those chiral fields by the compass contours. And we also need to add the new gauge singulars in the dual model. So this is the dual model. All of those models could be put in this way. So let me summarize the duality and action. So the first step is one need to replace every chiral field gauge like CD by a dual chiral field. Oh, this is like the field relation, what Julia just said. Just for those compass representation, you need just change the orientation. But for those real representation, just doesn't change anything. So in this case, we just have to see this stuff. And those dual fields are in the compass conjugate representation. The fundamental representation changes to the anti-fundamental representation. Okay, so this is the field, the first part of the field content in the dual model. And for the then we need to add the your gauge basically for each oriented loop starting flavor node. The associated the associated just gauge environment operate, gauge environment chiral operate. So here, for example, I can start here and then start with the C and the U, V arbitrary order, and then from D goes back. So basically, we just take a trace of those products and then get a gauging order. So operate this way. This way. So those kind of operators are called just method. Singular. Gauging right. And then here, because UV now is the matrices, so the ordering is important. So that kind of non-commutative. Very important. Ordering is so each such sequence will give us a chiral. So in general, we should have infinite such numbers, such higher operators, gauging event operators, because we can look at we can have an arbitrary kind of sequence here. So for each such operator, one at a single gauge single. And the transform the adjoint representation of the flavor group. Here I reduce the subgroup of flavor symmetry. Okay, this is the matter content of the dual model. Now, to make the duality work, there's a crucial constraint. As I said, if there's no constraint on the combination of UV, then we need to add the infinite number of gauge singlet. That will certainly wouldn't have a nice duality. So there's one thing that is very crucial is one need to have a truncation of Manhattan spectrum built from adjoint fields so there's only finite number of such choices. Finite number of such choices. Otherwise, there will be infinite number of such gauge singlet in your model. And certainly that wouldn't work. So this is one crucial constraint. And another ingredient, crucial ingredient in the original circular duality, one need to add a dual superpotential. The reason is the following: to have a equivalence of the inference theory, the space of operators, the gauge event operators, has to match. So on this side, we have this gauge event operator built from the fundamental fields C, U, V, and D, like right here. And on this side, we have a redundancy of event operators. We have gauge singlet, but we also have the operators built from the dual fundamental fields. So certainly there is a redundancy. So to match the chiral spectrum, we need to add a superpotential. So the fields, the composite gauge event operators will be projected out. This potential will project out. Composite metons, just metons. So this is this time put very strong constraint on the Mason spectrum, not just the numbers. So the number 2 ingredients requires the number of gauge-event operators in the original theory should be finite, and this one put the even stronger constraint. The reason is at the infinite point, infinite fixed point, all those terms should have a R charge 2. So to make all of those, to make all those terms to be to have a R charge 2, there should be a element between the spectrum, the random spectrum. Random spectrum. R charge, this is the R charge. R charge. R charge. We should pay it. Okay, any question?
That UI is
It's those mesons built from U and V's, the R charge. And this delta is a fixed constant. Okay, and finally, so I'll give some more examples, and then you will see what this means. And finally, there might be some massive fields because of those superpotential. Some of the methods may be massive, so one can integrate all those massive fields. And then we gather this is the contents of all the cyber duality and the cyber-like dualities. Dawson, Schreiber, Gordy, and last name. All of them takes this general form.
So what is the mechanism for this truncation? Is this by just a superpotential?
This is one way, and I will discuss this. Then another ingredient, one last ingredient, the dual gauge group. The dual gauge group is changed. We need to determine this dual gauge group. The rank of this dual gauge group. So basically, to make duality work, we need to impose 2 constraints on the Mason spectrum built from the U and the 2 constraints. One is such numbers are finite, and the other is the R charge of them should be paired. So simply from the requirement of possible duality, so we will find more constraints. Right now, just from this simple implication of what cyber found, we found the constraint. the by manual spectrum algorithm mean, we just talk algorithm mean the gauge events built from the adjoint calculus. So the two constraints. One, the number should be finite. And the second, the R charge. Should be paired. So the pairing of the R charges. And there's a fixed pairing constant.
So you have five lines attached on tree.
You can have many of them.
Oh, you have many. Well,
That's an indication that you have many of
the
them.
even number or odd number?
Arbitrary number. It depends on the
Or
models.
compare.
Depends on this number. This number is 8. The total for 8 such loops gauge signatures. Oh, then the only missing ingredient in finding duality is to determine this dual gauge group, the rank of dual gauge groups. And this one, this rank actually is easy to find. To find the, let's see, find, need to use the only great condition of the UR symmetry. So for every n equals 1 safety, there's such a spectral symmetry, asymmetry. And we know we can write down the anomaly easily. So in the original case, in the original theory, for T1, well, we have the equation. So these are the contribution from the adjoint carrier fields. Those are the contributions from the fundamental fields. And this so this is the one this is the contribution from a Dirichlet. So there's the constraint between the R charges of the fields CD and the UV. That's one constraint. So we can find the R charge of the fundamental fields, and by symmetry, the R charge of C and D should be same. So which I already used this fact. So first one can use A maximization to verify this equivalence. So from this equation, the R charge of the fundamental fields is determined by is fixed by the R charge of the adjoint fields and the other data rank and label number. Now we have a pairing between this mesons, and remember we have a superpotential which takes this form. So that means each term has R charge 2 at the fixed point. So that means we have an equation RC, 2 RC plus R. Now we use the pairing condition, we can determine the due, the R charge due carrier field in terms of the original carrier, the fundamental carrier field, and the pairing constant. This comes from this pairing and the marginality of the due superpotential. And then finally, we look at the duality. So this is one equation. Second equation. Then the third equation coming from the marginality. The normally free condition, the Q are solution. So very similar, exactly the same as this one, except we need to use the new data, like you say pi, to get now I have to emphasize the fields, the R charge of the adjuncts does not change. They'll be the same in the original theory and the field theory. Combine those three equations, you get the due of the rank of the due gauge group. It's this general form. This then completes the determination of the field theory. And this constant A, which determines the field gauge group, is given by, it's fixed by the pairing constant of the mesons and the R charge of the adjunct field.
Is that an integer? A?
Yes. It has to be, it's actually integer. And it's actually, in all the cases, they're equal to this number, which is not obvious.
Is it same as A in the 40M1 theory? A and C, there is an anomaly quotient there. That's different.
Yes, it's different. It's just a constant. It's just constant. Nothing to do with the center charge. Yeah, I'll talk about center charge later. That will put them more constant.
So you're saying that A is also a number of methods?
Huh? So yeah. These two numbers seems to be equal. which is not obvious at all. Perhaps I need to give you some examples. I will summarize the examples discussed by previous people. They all fit into this framework, general framework. Now, for segregated, there's no adjoints, just as QCD. So we have a delta equal to 0 because there's no adjoint mesons, and A should be A just equal to 1. Identity, there's one identity. So we have A and UV equal to 1. So we can integrate them out. So they're just massive. They have R charge. We can add a master. That means the meson spectrum, the just meson. So just one, just see. This is one. The R charge is 0. So A using this formula, we find A is equal to 1. A equals 1. Okay. And the reducible potential is W equal to CD. This is just a single term in the reducible potential. So that's the original circuit. So Schweimer duality the superpotential, there's a superpotential. Original electric theory is a superpotential. And then we find the meson spectrum ET. Just doing the derivative of that. So the meson would be 1, okay, minus 1. And the charge of V is 2 over K plus 1. So indeed we find a pairing between the mesons, and the pairing constant is K plus 1. Like 1 paired with the Vk minus 1, V pairs with the Vk minus 2. And the R charge of them, just the R charge of the Vk minus 1. So we have the in the electric theory. We have a meson. C. And then we substitute those charge U, the charge U, the R charge of U is just 1, charge of V is this number. We substitute those numbers into the formula, we find A just an integer, and it's just equal to K. That is exactly equal to the number of mesons, the total of K. And the dual theory would have also would have a K. K singulars. And this is the K and F minus MC. So that's the equivalence of Schweimer.
Left is box, right? Not the circle.
This box. Flavor. Okay, then the next one.
Sorry, is this R charge consistent with A mathematician? In this case,
You don't have any
and
choice. It's fixed by this equation.
Yeah.
You don't need to do anything.
So what is the paradox of potential that involve U stuff?
The same.
The same. U stuff.
Yeah, there's a way of I didn't say in a full generality. For the dual superpotential, you change the original. So originally you may have some superpotentials, and in the dual theory, just replace those fields by the dual fields. That's the general rule.
Part about method.
What?
And then add the part involving method.
Yeah, gauge singulars. Gauge singulars. Yeah, you need to keep the original and pass the actual. And then we have the much less known, the one discovered by Gordy. And he considers so-called BK superpotential. We can find the truncated. We can find the spectrum by doing derivative. The truncation is the following way. We have two equation motions. The equation motion from superposition. One must be a little bit careful because these are the non-commutative variable or the matrix. So this matrix must be careful. They're not the same. UV and VU are not the same. Okay, and then we can have the spectrum. The spectrum from U. Now this equation, just look at those two equations. So this equation means the UV and the VU is anti-commutative. So you can arbitrarily change your order. Just change a sign, minus sign. And this one means v squared is given by uk. So we don't need to consider v squared. Or UK. In other words, UK is fixed by v squared. So we don't need to consider all the UK. So therefore we have this. At least those are the part of the spectrum. Meson spectrum. They are here. But they're not necessarily the full set. Because let's consider we can multiply v on this equation and then using the first equation. And then we get the equation of dq. And finally, we find that dq equal to 0 if k or no constraint. So this means is that if we impose this d-type superpotential only for k odd, we get the truncation of the Meson spectrum. And indeed the pair, we easily check them. Indeed pair, we will have the data. What we need is the data. And the pair constant from this set. And then we get a dual, the rank of dual. So this is our A equals k, which is also equal to the number of truncated meson for k odd. That's much less well known duality, body duality, which fits in the framework I just discussed.
So I think that this duality only works if k is on.
Okay, that's the remark that I'm going to talk about. So in his book, in his paper, Bode also suggested the duality also works for even k, Although classically we do not have such a truncation, and he suggested that such a truncation might arise mechanically. But I believe even today, I don't think any people come up with some nice explanation of how such a quantum constraint arises. But if you take such a truncation, forget about the superpotential. Just take this truncated spectrum, then everything works. You got it? Everything. The match of Madison spectrum. I probably do not have time to talk about the bionic spectrum and the central charge. What those things are matched. All of them are matched. So I think people believe that even for even case, there might be a quantum constraint to truncate the Madison spectrum to the form that I just put down for even or odd case. Okay, so finally, let me talk about duality. What they discussed is simply change the superpotential to the so-called 7. And they have to impose classically, we certainly do not have a truncation of Madison spectrum. So they have to impose a quantum constraint. And the truncation in all language is very easy to impose them. We just need to impose this pairing and UV and fixed. In our case, we have the data to charge U to source, V, and the pairing constant, this number. And then we find A equal to 30. So the dual gauge group, the dual theory will have a total of 30 gauge singlets. And this is the 30, then the
So how does the R change becomes 2, 4, or 9?
yeah, the total R charge should be 2.
2, right?
Yeah, for the superpotential, the R charge of the superpotential.
But U and B is that the R charge, right?
R charge, yeah.
Because the quantum constraint it becomes 2 somehow.
No. Those are just fixed by the superpotential. Each term should have a R charge 2.
Right?
Yeah. So you
why 4, 1, 9? It's B.
Sorry, I think I read it wrong.
Oh, okay, that's why. Okay.
This is mistakes. And unfortunately, for people might have known that there's AD classification. Unfortunately, for E6 and E7, E8, it doesn't work. There's no way to find a dual duality like what I explained. I have less than 10 minutes, so I'll go to the main part. So as I just described, it seems that one can have a duality if the R charge of the mesons formed by adjoint fields take the two requirements. One, they should be truncated, the finite set, and the R charge of them should be paired. And it turns out we need to have much more constraint other than that. So for example, we need to verify that the superconformal index should match. That puts a much stronger requirements. And also, we need to verify the central charge BC should match. Or in N+1 case, we just need to check the trace R and the trace RQ along the image. So especially this one. Now this is a cubic function for the R charge. It's not easy to satisfy. The superconformal index turns out to be very useful. Actually, other people already studied that. And up here, I just summarize the result. So we have a assuming our duality, assuming the model takes this form, and then one can just compute the superconformal index in the so-called with the envelope limit for the large and say prime has limit. You just compute also the contribution of the fields. Just compute the superconformal index in the large and say limit, and then to make them equal, it turns out that we have the following equation of the R charges. So this is the most important equation. So just compute that's another part, actually, other very hard computation. and then to make the index equal the R charge. So those are R charge from the adjoint fields. Those are the R charge from each singlet. And this is the pairing constant. So as long as those data, the R charge of UV and the R charge of the gauge singlet for the truncated meson, truncated meson spectrum R charge. If they satisfy this equation, it seems that those numbers also match. The number also match. And then the problem, we can go backwards, because in all framework, to make duality work, all we need to know is the R charge of the tensor field and the mesons and the pairing constant. As long as we have those data, then we have a duality. That means, look at this form. The possible new models reduced to the factorization of this polynomial. Into a positive part. So this term is all positive. And move this term here. So the positive term times the negative term. And then we immediately have a so large of very large possibility, large space of possibility. Then the most the remaining question. Can we realize physically? Turns out in any case we cannot previously the only way to truncate the possible spectrum through superpotential, but from our discussion about the well-known duality discovered by Brody and also me, certainly we cannot just be constrained to the truncation by superpotential. We certainly need to open our eyes and look more broadly. So that's a main question. So certainly from this factorization, we can find a very large class of models which have their duality property, but we need to understand how to realize such spectrum. All right, I think finish. Thank you.
Any questions?
I want to ask about the dimensional reduction. Is it possible?
Yeah, of course, you should one can consider three-dimensional symmetry. But of course, technically, details should be much more different. But the idea should be similar.
Suppose you, for the theory and the dual theory, both have some flavor ambiguity to determine the R charge of some fields. then you can separately do the A maximization for both sides. Is this obvious still consistently to those R charge you determine how?
I think once you here, I didn't really address the issue of the whether there will be accidental symmetry or things like that. But my feeling is that the duality is sometimes more powerful. The duality to tell what's going on. But certainly, this is right now it's just a combinatorial game. But certainly some interesting dynamic perspective. Okay, answer. Try to answer.
When you consider the superpotential of both sides, why you take the large limit?
Superconvolution
index.
Because it's easy to compute.
But if you keep finite NF, will you get more constraints?
I'm not sure, so you can try to compute. See whether you get more constraints.
You just mentioned that some of the theories cannot be realized easily. Maybe they're just not consistent. If you consider the constraint with finite NF.
Personally, I think probably finite and CNF would not. When we compute the central charges, we compute the finite and CNF. Actually, exactly, but they all match for central charge, which is very non-trivial. Because the R charge has to satisfy more constraints, cubic or projective equation, but they seem to all satisfy. For finite and CNF, we compute the central charges. They all match.
The supercomputing index contains more information than central charges.
Yeah, sure. Yeah, we can try to cover finite values. Finite and CNF to say whether they're more constrained.
Factorization of that kind that you know will not go from the any group here.
I don't know. I'm not. I don't know. We just know so little for angles. So I cannot say whether they are allowed or not. That's why I said can we realize them? Yeah, even for the the D-type superpotential even ones or the plus, we don't know how we can get such a how is that possible?
Any other questions?
From this duality perspective, is there any hint for, you're always staying in this conformal bounds, this client bounds?
Well, for duality problem, I don't think you need to be constrained. So from the experience of cyber duality, just go beyond the conformal window still works. It still works. So that's why I think duality is more powerful. Sometimes more powerful than dynamic consideration.
So could you please explain more detailly why we should repel the autotrophs to be paired to make the duality work?
Why should we pair?
Yeah.
No, because I said we need to add the superpotential, so the spectrum, the gauge spectrum should be matched. So that's the easiest way to satisfy this constraint. That's the easiest way. Otherwise, if you have such a large number, and then if they're not paired, then it's very hard to satisfy this condition. So all the R should be 2. That's the easiest way.
Can you find ways to make this equation satisfy?
Might be, but that's not a systematic way to do it.
Any other questions? If not, let's thank Dan again. So there's a canteen over there, but only